So okay students, title of today's lecture is spreading resistance measurement. So first we will see what is spreading resistance and how we can measure it, and then we will see its application in doing the depth profiling in case of semiconductors. Now first let's see what is spreading resistance. So you have seen this kind of diagram many times. So actually when we perform any measurement with the help of any probe, so probes touching the semiconductor, so you see this is semiconductor surface and these two probes are used here. So the current is entering through this probe and current is going out through this probe. This is two probe measurement, and we measure voltage here between these two probes. So what happens actually when this current enters into the semiconductor material, the current is concentrated at the probe tip, right? So for example here, if this current is entering, you can see its enlarged view. What happens here at the top, when the current enters into the semiconductor, it spreads like this, and this spread is outward. See, the current is entering at this point, and from this point the current is going outward like this. It is moving in all possible directions. So this spreading happens here at the interface inside the semiconductor, and that's why this current is known as spreading current. And whatever resistance is offered by this interface and this portion of semiconductor to this spreading phenomena, that resistance is known as spreading resistance. And it's very important to find out the spreading resistance because it affects lot of other measurements also. And sometimes the spreading resistance measurement itself is a tool to find out some important information about the semiconductors, and that we are going to discuss today. So when we perform this kind of measurement, so we know that our resistance, if you want to calculate between these 2 points, then this resistance from Ohm's law is ratio of voltage to current, and that net resistance between these 2 points is given by this formula. So you already have seen it many times. 2 times probe resistance offered by these 2 probes, 2 times this contact resistance, means the resistance offered by this contact and this contact, plus 2 times spreading resistance. Spreading resistance is the resistance which occurs here. So spreading occurs here and spreading occurs here at these 2 points. So this is the total resistance which we can find out using this formula. So remember here we are ignoring the resistance offered by this piece of semiconductor, because when we do this kind of measurement of measurement of spreading resistance, so we make this sample and this entire setup in such a way that the resistance offered by this piece of semiconductor is very small. So what actually happens, not only the resistance offered by this piece of semiconductor plus the other components of resistance like this contact resistance, this probe resistance is already negligible. So this contact resistance is also made negligible. Contribution of the semiconductor towards this total resistance is already negligible. So that's why it is not considered here. So what dominates? This entire measurement dominates only the spreading resistance. So whatever resistance we are measuring using this setup, that resistance will give us 2 times spreading resistance because we are using 2 probes. But remember, it happens only in particular situations when we make this arrangement in such a way that the resistance of the semiconductor is negligible as compared to spreading resistance, and the contact resistance also is very small as compared to spreading resistance. So if all these becomes negligible as compared to spreading resistance, then this total resistance whatever we are measuring, that is our spreading resistance, right? So this is a mechanism through which we can measure the spreading resistance by making all other resistances negligibly small, right? Now the values, the meaning of RP, RC and RSP, you already are familiar with these names, and they are summarized, they are mentioned here also. Now so now before going further, we must understand that at least theoretically we must understand that on which factors the spreading resistance depends, or what can be a theoretical formula that we can put into that equation to have more detailed understanding about the spreading resistance. So for that we will see now. So we will see that when a probe touches a semiconductor, so how we can theoretically calculate its spreading resistance, or how we can estimate the spreading resistance. So you see, when a current I flows from a probe of diameter 2r into a semiconductor of resistivity rho, So for example, these two cases we are taking for two different shapes of the probe. So if this case you see here, so this is a piece of semiconductor and this is a probe which is touching the semiconductor, and this is interface. This rho is the resistivity of the semiconductor and 2R is the diameter of this piece. So this D is shown here, this D is equal to 2R. Now what is the difference between these two cases? The difference is in the shape of this tip. So here this is flat tip, so this is a non-indenting tip, right? Non-indenting means it's not penetrating into the semiconductor. This is a flat surface. Of course this contact is cylindrical contact. If you see this 3D picture, so this is a cylindrical probe, but this top is flat with a planar circular interface. This interface is planar, right? In this case this is a hemispherical. So this tip is designed in such a way that it is hemispherical at the end, and indenting tip means it is penetrating into the material, right? And here also radius is R. Now these two situations will offer a different kind of spreading pattern into the semiconductor, because here you see it's a flat, so it gives a different kind of spreading pattern, and this will offer a different kind of spreading, right? So because the pattern of this spreading current is different in these two structures, the spreading resistance value will also be different, and the spreading resistance value can be estimated using this formula. So we are not going to discuss the derivation of these equations in detail. You just have to remember that formula for spreading resistance in this case of in this particular case, when there is a flat contact, is given by this, and spreading resistance when there is a hemispherical shape at the end of the tip, then the spreading resistance will be given by this formula. So you can see using both these equations, the spreading resistance is inversely proportional to the diameter, or you can say the radius of the probe. So if radius of probe is small, this spreading resistance will increase, and the spreading resistance also depends on the resistivity of the material, right? So if you can experimentally find out how much is spreading resistance, and if you know the diameter, it's also possible to find out the resistivity of the semiconductor, because this rho is the resistivity of semiconductor. So sometimes this 4 probe measurement is also used to find out resistivity. So your resistivity you can find out with the help of 4 probe method also, but the spreading resistance measurement also gives you an additional tool to find out the resistivity of the material, or resistivity of the sample, right? Now once you understand that spreading resistance depends on these kind of factors, then whatever resistance you measure here in case of a single probe, that net resistance, so we have seen in the earlier slide also, for the single probe setup, so net resistance is the contact resistance plus spreading resistance. So don't get confused. I am not saying that whenever we will do measurement we will use a single probe setup, because with a single probe we can't do any electrical measurement, we need at least 2 probes. So this equation, I am saying that this equation is written only for the case of a single probe. So if we are using this setup for doing some measurement, of course we will use 2 probes, and in that case there will be 2 here and there will be 2 here. Contact resistance and spreading resistance will come into picture. Remember, I am assuming that the resistance offered by the semiconductor is negligible, right? So we can write it like this also. So the spreading resistance is inserted here. So because we don't know this case or this case, but for both these cases it's rho, and it's inversely proportional to radius, right? So we can write it something like this. So what is C? The C is correction factor. So the correction factor depends on many factors, but again I am telling you that we are not going to discuss correction factors for the spreading resistance measurement, right? So now the measured value, I told you in the last slide also that it will give you only the spreading resistance provided this contact resistance is small, right? And the spreading resistance becomes large if this R is small. So if you want this factor to dominate over this factor, and this is something which we want in the spreading resistance measurement, we have to reduce this contact resistance and we have to increase this contact resistance. So this factor should increase and this factor should decrease, and that we do because we want to express this value as much as possible. So if you want to increase this value, what you can do? Reduce the value of R. The probe should be of very small diameter, as small as possible. So that way you can reduce, that way you can increase this component, right? And if you want to reduce it, for reducing this contact resistance, so you know contact resistance depends on the barrier height here, and the barrier height depends on the combination of this metal and semiconductor, and that barrier height also depends on the doping level here into the semiconductor material. So if you want to reduce the contact resistance, then you should reduce the barrier height, right? And if that happens, then this contact resistance becomes very small as compared to this factor. Now normally what happens, if you make this contact resistance very small, this spreading resistance will increase, right? And this factor will increase, and that's what we want. And we can predict that the spreading resistance is approximately 2500 times the resistivity of the material, right? And that's why the resistance offered by this piece of semiconductor will be negligibly small as compared to spreading resistance. And this contact resistance is also made low by reducing the barrier height here at the interface. But okay, so in that case it dominates over RC. But you know, if metal semiconductor barrier height is significant, and it happens in case of gallium arsenide material because it's semi-insulating material, and its band gap and all these things defines the barrier height. So in case of gallium arsenide, this barrier height is significant, so you cannot ignore it. In that case, the measured resistance does include a non-negligible contact resistance. So in that case, the contact resistance is not negligible. In that case, it is difficult to isolate this spreading resistance, because whatever resistance you are measuring, this contact resistance is also not negligible. So you can't say that measured resistance is this component spreading resistance. But in case of silicon, the barrier height is not that much high, and that barrier height is reduced further by increasing the doping into the material. Because of the small barrier height possible in case of silicon based systems, so it's possible to make this contact resistance very small. But remember, it should be not just small, it should be very small as compared to spreading resistance, so that this measured value gives us only spreading resistance. Now you have seen that the measurement we do with the help of this kind of two probe setup, and if the barrier height here, barrier height of this metal and semiconductor contact is chosen in such a way that it's very small, this contact resistance will be very small, right? And this is of course negligible, it's nearly zero, right? So in that case, whatever resistance we are measuring, that is your spreading resistance, right? And of course, this piece of semiconductor is also offering very less resistance to you, right? Now, mainly if you see this spreading resistance, so 80% of the potential drop due to this current spreading, it occurs within a distance of about 5 times the contact resistance. And in the last slide, we saw one example that the contact radius is about 1 micrometer. It means if it is 5 times, means within a distance of about 5 micrometer, the spreading resistance will drop. And if the spreading resistance is dropping within this 5 micrometer and within 5 micrometer here, it means if we want the effect of spreading resistance to dominate here in this equation, these two probes should be very close to each other, right? Only then the spreading resistance component will dominate here. So see, within a distance of 5 times the contact resistance, the effect of spreading resistance goes down, right? So that effect should dominate. So these two probes have to be placed very close to each other. So the probe tips are shaped in such a way that they can be positioned very close together, and often this gap between these two probes is less than 20 micrometer. You know, in case of 4 probe setup, gap between these probes is about 150 micrometer, 150 micrometer. It's it's more than this. So the gap is 0.15 centimeter, something like this. It is in centimeters, a centimeter or millimeter, right? But here this gap is very small. It is less than 20 micrometer, right? So that the effect of spreading resistance stays here in this equation. So now you understand what is spreading resistance, and if you want to measure the spreading resistance, we have to use a 2 probe setup, because if we use 4 probe setup, the effect of spreading resistance doesn't come into the equation. We have discussed it while discussing the 4 probe method. So if we want to measure spreading resistance, we should go only for 2 probe setup, not for 4 probe setup, because we want spreading resistance effect to dominate in the measuring equation. And for that also, we have to ensure that the contact resistance becomes very small by choosing a combination of materials in such a way that the barrier height is as small as possible, and the spreading resistance should be made large by choosing a probe diameter or probe radius as small as possible, normally 1 micrometer. Further, the third step is the gap between the 2 probes should be as small as possible, so that the effect of spreading resistance is dominating between these 2 contacting probes, right? And that way we make that spreading resistance dominates here, and the measured resistance between these 2 probes is just spreading resistance and nothing else. Now we will see that what are uses, what type of benefit we can get out of this spreading resistance technique, right? And before that, we will go to another point. So we will see a topic, resistivity profiling, and then we will see that how this spreading resistance profiling or spreading resistance measurement is very useful in doing this resistivity profiling. Now what is this resistivity profiling? You see, most of the time resistivity varies as a function of position. For example, if we have a silicon wafer or any kind of sample like this, so at different locations on this, we may have different value of resistivity. That kind of non-uniformity can occur if your doping system is not well controlled, and sometimes that kind of non-uniformity is intentional, right? So that kind of measurement at different location, measurement of resistivity at different location is resistivity profiling. But most of the time we are not interested in this lateral profiling, we are interested in the vertical profiling. For example, you see this kind of sample. So a thin layer is deposited on the top of a insulating material, right? And the thickness of this top layer is T, and we may be interested to find out how its resistivity changes when we move down, right? So at the top surface it may have a different resistivity, and when we go inside, its resistivity may change with the depth. In what kind of situation it may happen? For example, if we have a diffusion or ion implantation we have carried out here, and then we want to find out its profile, means how the dopants are changing inside the material when we go down. So its resistivity will change. So because in case of diffusion, you know that at the top there are more dopants, and as we go inside down, then the dopants decreases with distance or with the depth, and so the resistivity will also change when we move from top to bottom. So most of the time we are interested to do this kind of resistivity profiling, and this profiling is in vertical direction from top to bottom, right? Sorry. Now resistivity profile of non-uniformly doped layer cannot be determined from a single sheet resistance measurement. You know, in case of 4 probe you can perform a sheet resistance measurement, but a single sheet resistance measurement will not give you that kind of profile, right? If you want that kind of profile, so what you have to do, you have to repeat this measurement at several locations if you want to go in the lateral direction, and if you want to go vertically down, then what you have to do, on the top you do one measurement, then remove a small thickness, then you again repeat a measurement, then you remove a small thickness, and then you repeat. So that way you have to have a multiple data at different locations in order to do that kind of resistivity profiling. Means the resistivity as a function of depth, that data if you want to get, then you have to repeat this measurement at different locations. And remember, sometimes we are not interested just in finding the resistivity as a function of vertical position. Most of the time, instead of resistivity, we are interested in dopant density profile. Means, for example, when we do diffusion, so what we want, how many dopants are here and how many dopants are here as we are moving down. So what we do, we find out resistivity at different locations, and you know that resistivity depends on the doping density. So from that resistivity data, we calculate the doping density. So that way from resistivity profile we generate dopant profile. Now we will see that how this spreading resistance is helpful in doing this, and we are not interested in a removal of material after every measurement, but the spreading resistance measurement technique can give you a very perfect way of doing this kind of resistivity profiling. So resistivity profiling you can do with the help of spreading resistance. That's the only thing which I want to say. But remember, it's not just resistivity. We can convert this resistivity profile into a dopant profile. Now you will see here there are many techniques which you can use to find out the profiling, resistivity profiling. So these techniques are compared here. So for probe also you can use, right? And the spreading resistance is here. So these three techniques maybe you have not seen, but spreading the 4 probe method you already know, spreading resistance you know. So and these first 3 techniques are electrical techniques, and if you compare these techniques, or if you compare all the 4 techniques, you see first 3 are electrical, they are optical technique. And if you compare resolution, for example, you see here 3000 micrometer, here 3000 micrometer, here 5 micrometer. So these techniques, this technique give you very good resolution, but right now we are not interested to discuss this, because these are optical techniques and very sophisticated instrument is needed for them. We are focusing on the electrical techniques. So for probe you know, so here you see resolution is 3000 micrometer and here resolution is 5 micrometer. It means you can repeat this measurement, or you can get data at a gap of 3000 micrometer. So if you have a sample here like this, so you have one data here, you have one data here, you have one data here. So the 4 probe have flexibility that you can get this data at a distance of 3000 micrometer. But spreading resistance gives you far better flexibility, far better resolution. It means you can get repeated measurement just at a gap of 5 micrometer. So very good resolution is possible as far as electrical characterization techniques are concerned. So that's why spreading resistance is widely used in case of resistivity profiling instead of 4 probe method. So other parameters also you can see here. So all these things are very obvious to you. So just the major difference here is the resolution, and that is very important and very useful difference, and it gives a sharp edge to this spreading resistance method for finding out the resistivity profiling. Now we will see how we do this resistivity profiling. Now originally what happened, the lateral resistivity variation determination, that was done with the help of the spreading resistance profiling, and it is mainly used today to generate resistivity and dopant density depth profile. So I told you that resistivity profile, and from resistivity profile we can generate doping or dopant density profile, and the spreading resistance profiling SRP technique is widely used for that kind of thing. And the sample preparation is a very typical process for this SRP measurement. SRP means spreading resistance profiling. If it it's a very complicated thing, and you need a well controlled setup to create a sample for this kind of measurement.
It depends on your system which you
are
using
can
for
see from
measurement.
So that kind of setup is used. So this is substrate, and on the top of this substrate there is a film here, and within this film we have to find out the dopant profile or resistivity profile. Means
and remember this part
at different locations here, at
just
different
you have
locations,
to know the value of
vertically. So we need to know how much is resistivity or how much is doping here. So at these points vertically, so we need to do this kind of measurement. So what we do normally here, so this instrument consists of 2 carefully aligned probes. So these 2 probes, I told you, for spreading resistance measurement we have to use 2 probes, because 2 probe setup have spreading resistance component. 4 probe setup doesn't have
get more accurate results
component.
from this equation, because the sample is not semi-infinite all the time.
2 probes, they are
and
stepped.
In that case we need to add
step means
factor into this equation.
These 2 probes, they move from one location to other location,
in the next lecture.
and this movement is horizontal movement.
Goodbye.
So you see here the beauty of this setup is that we want this profiling vertically, but actually the two probe setup that is moving horizontally. It's because this system or the setup is designed in such a way. And we use a beveled surface, so a sloped surface. So what we do, so this film is deposited on this substrate, but this top film where we want to do this profiling, this film have a slope. The slope is created here, and this slope is very small slope. So practically you will not be able to observe it. If you view the sample from the top, you will not be able to observe this slope here. Why? Because the angle here, this angle theta, this theta is very small. This theta is about 1 degree or something like this. And then once you have this kind of slope, then this sample is positioned in a measurement apparatus with the bevel as perpendicular to the probe spacing direction, probe stepping direction, sorry, and this angle is 1 degree or something like this. So that's what I was telling you. So actually what happens, so this entire sample is tilted. So after creating this kind of slope, the angle is 1 degree. So here also you can see this angle is about 1 degree. So if you see here, if you extend it like this, so this angle is 1 degree, or this angle here also it's 1 degree. And this entire arrangement is tilted little bit in such a way that the probes, they are moving horizontally. So this surface, this entire surface is perpendicular to this probe. The probe are perfectly vertical, and this is perfectly horizontal. So this entire arrangement is tilted in such a way. So actually what is happening, the probes are moving in the horizontal direction. So we are doing this measurement of resistivity at this point, at this point, at this point, multiple points, but effectively we are getting data at different depth. Because if we talk about this, so you can say if we are measuring this data here, so this is like if you draw a line here and then draw a parallel line here, this is actually here, right? So if you want this measurement here, it means when you are getting data at these horizontal locations, so effectively the data is from this particular depth. So that kind of arrangement is there. So this sample is moving, these probes are moving horizontally here because the sample is tilted by 1 degree like this, and but effectively because this part is sloped part, so effectively this horizontal movement is converted into this vertical movement. Now see, for example, now if theta, this theta is 1 to 5 degree, then the junction depth 1 to 2 micrometer is possible. So if it is 1 to 5 degree, then it's possible to do this kind of profiling from like 1 to 2 micrometer depth, right? So this is junction here. So this is another kind of maybe p type, and this is n type. Substrate is n type, or substrate is p type, then it is n type, right? So we are doing this profiling within this portion here. But if this theta is very small, 0.5 degree or something, then the junction depth, so means the depth up to which you can do this kind of measurement, that depth also decreases. And you see how they are related. So they are related using this formula. So the equivalent depth z is this vertical depth, and this x is horizontal movement. So this is delta x. If you are moving like this, this is delta x. So delta x is the gap between these steps, and delta z is the vertical movement. So if you can draw a line here like this, right? So now this is your z. Delta z is small gap here, and this is your theta. This is theta, and this is your delta x or x. You can say this is delta z, right? So this delta z from trigonometry knowledge you can see here, right? So how much vertical resolution we can get here, it of course depends on this horizontal resolution also, means how close measurement we can do, and that can be translated into the vertical movement. For example, if this angle is 1 degree, and the step is 5 micrometer. So I told you that in case of spreading resistance, resolution is 5 micrometer, means within a gap of 5 micrometer we can repeat the measurement. So if that happens here, we put here 5 micrometer, we put here 1 degree, then the delta Z is about 0.87 nanometer. Means for 5 micrometer distance which we are traveling here, just because of this design, vertically we are getting very high resolution, 0.87 nanometer. Means we can get this resistivity information at a gap of 0.7 nanometer, every 0.87 nanometer. So we have here in resistivity value. So after a 0.87 nanometer depth, again we can get new value, and that way we keep on repeating. So this gap should be as small as possible if you want very high resolution, and this much resolution is a very good value. So, and that is possible because the spreading resistance measurement which we are doing here on the horizontal surface, that is giving us a resolution of 5 micrometer, right? If we do this with the 4 probe, we will not get spreading resistance, of course, but the resolution is also not that much high. If you want to find out just resistivity, the resolution will not be that much high. I hope that you get enough idea that how this kind of measurement is done. Now another important thing is that it is very useful to provide sample with the insulating coating. So the sample top layer should be insulating layer. So it gives you several benefits, because I told you that this angle, slope angle, is so small that when you look at the top surface, you will not be able to observe that when this slope starts, right? So if this happens, then it is useful to have a insulating coating on the top of this. Why? Because when what happens, the oxide provides a sharp corner at the bevel, and also the clearly defines the start of this surface because the spreading resistance of the insulatory side. So when you repeat the measurement here at different locations, so because there is an insulating coating here, during the measurement, 2 probe measurement, you will not observe any current here in the system. So you will come to know that right now you are at the top surface. So once you repeat this measurement at different location, once you reach here, suddenly you will feel that current starts flowing here, because this part doesn't have oxide on the top. So semiconductor is exposed here. So suddenly you will get the reading of the current, and you will come to know that you are now at the point where you are getting actual readings, right? So it's useful to have this kind of coating here. Now suppose you don't have this kind of coating here, then also there is a possibility or a solution of the problem. So what you do, you start the measurement at least 10 to 20 points before this bevel edge. So before starting this edge, so 10 to 20 points before you start the measurement. So what will happen? So at all these points you are at the top. So the doping is same here. So resistivity which you are calculating, that is also same. So you will see that okay, there is no change in the reading, but once you reach here, suddenly you see that the resistivity is changing, or the current in this setup is changing. So you will come to know that now we are at the right portion from where we have to start the readings. So these are the 2 ways that one is that you should have a top layer, oxide layer here on the top, and second is if you don't have oxide layer, start like very early from this, so that once you reach here, you clearly see change in the readings. Now another important thing which you should keep in mind, that when you do this spreading resistance measurement, perform this measurement in the dark, because in the light you will have some photoconductance, and because of that there will be change in the doping in the free carriers here, and the resistivity will also change. So whatever you are measuring, that is not the true value of resistivity of the sample. So you are getting effect of the photons, and that is something undesired. Now you have a clear idea that how to do this spreading resistance profiling. But I told you that it's not that only the resistivity is important. We are not only interested in the resistivity profiling as a function of vertical position. So actually we want to find out the dopant profile. So how to find out this dopant profile? So once you know the resistivity at different depth, you can calculate from that resistivity value the dopants which are present here in the material, and for that you will find many equations depending on the type of material, depending on type of conductivity and these kind of things. So here if you see here in this graph, you see the measured resistivity profile data can be converted into doping profile. So here it's depth. So 0 means we are the top, we are on the top of so suppose this is sample and we want to do this measurement here. So we at the top, if we are here, then it's 0. So when we are going here like this, so we are moving towards this 0.1 micrometer depth, up to 0.1 micro depth we are getting. And this blue line is spreading resistance. You see, when we are going inside this, we are vertically, we are going down, this spreading resistance is increasing, and the spreading resistance increasing means the dopant here, we are going down, the number of dopants here are less. Maybe it's a diffused sample, and a diffused sample, you know, on the top number of dopants are more as compared to bottom layers. So when we go inside the material, resistivity will keep on increasing like this. So this blue data is like axis for this for reading this blue data is here. This is spreading resistance. So the spreading resistance is increasing like this, and from the spreading resistance theoretically we can calculate how many dopants are there, and the calculated value of dopants is given here in the red line, and the scale for this is here. You see here, when this resistivity was very low at the top, the dopants were very high, right? And as we are moving inside, resistivity is decreasing. So dopants are resistivity is increasing here. So the dopants are decreasing here like this. So whatever value of resistivity we are getting as a function of vertical position, so that value can be used to find out the dopants at that particular depth. So that way we get the doping profile of the semiconductor materials or thin films. And the good thing is that this spreading resistance technique gives very high value of reproducibility, and the reproducibility is problem here. So it can be like 10% can be obtained routinely by qualified RP systems. So this reproducibility is an issue here, and high reproducibility is something which we desire, but this issue is certainly a concern, because most of the time reproducibility which we get in case of spreading resistance profiling is about 10%. So I hope that I'm able to convey this message clearly to you, and now you understand what is spreading resistance, how we can find out the spreading resistance, and how this spreading resistance can be used to find out the profiling or to do the depth profiling. And remember, if you want to find out spreading resistance, this kind of equation is sufficient. So just you have to see how much is the resistance, and from here you can find out, if you know the resistance, you can find out this rho, resistivity of the material. So thank you very much, and in the next lecture we will meet again with a new topic, right? Thank you very much.